In metallic conductors, the valence electrons are free to move about the metal without leaving the metal. These electrons are referred to as free electrons. The conductor is said to be in electrostatic equilibrium when there is no net motion of the charges in it. Some basic properties of conductors that are in electrostatic equilibrium are: the electric field inside a conductor is zero. The interior of a conductor can have no excess charge in the static situation. At the surface of a charged conductor, electric field is normal to the surface at every point. Magnitude of the electric field strength at the surface of a charged conductor is E equal to sigma by epsilon naught. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. A cavity inside a charged conductor is electrostatically shielded. Now, let us look at each property in detail. One, electric field inside a conductor is zero. Consider a conductor whose free electrons are distributed uniformly throughout. Let us now place this conductor in a uniform external electric field of strength E directed towards the positive x-axis. When the external electric field is applied, the free electrons in the conductor accelerate towards the left. This causes a plane of negative charge to be present on the left surface. This, in turn, causes a plane of positive charge to be present on the right surface. These planes of charge create an internal electric field whose strength is denoted by E dash, opposite to that of the external electric field. Within a short interval of time, the surface charge density of electrons present on the left surface increases, until the strength of the internal electric field becomes equal to that of the externally applied electric field strength. As a result, the net electric field strength inside the conductor becomes zero. It proves that any net charge on the conductor must reside entirely on its surface. 3. At the surface of a charged conductor, in electrostatic equilibrium, the electrostatic field should be normal to the surface at every point. To prove this, for a conductor in electrostatic equilibrium, let us assume that the electric field E due to the charged conductor is not normal to the conductor but as directed. In that case, it will have a component parallel to the surface of the conductor. Then, the free charges on the surface would experience some force and move along the surface. 4. Electric field strength E at the surface of a charged conductor is equal to sigma by epsilon naught into n cap. Let the surface charge density be sigma. We know that the surface charge density is defined as the charge per unit area of the surface. Surface charge density is equal to the ratio of the total charge on the surface to its area. Let us consider a Gaussian surface in the shape of small cylinder, which is part inside the conductor and part outside the conductor, such that its flat faces are parallel to the surface of the conductor. Since the electric field strength at any point just outside the conductor is normal to its surface at that point, we do not have any electric flux through the curved surfaces of the Gaussian surface chosen. We also know that electric field strength E is equal to 0 for any point inside the conductor. And hence, the electric flux through the Gaussian cylindrical part inside the conductor is 0. However, there is electric flux through the flat face of the Gaussian cylinder just outside the conductor, as the electric field strength E is perpendicular to the flat face. According to Gauss' law, the electric flux phi through this area will be equal to integral E dot dA. Here, integral E dot dA is equal to integral E dA cos theta equal to integral E dA, where cos theta is equal to 1 since the angle between the vectors E and dA is 0 in this case. Since E is constant through the flat face of the small Gaussian surface chosen, we have phi equal to E into integral dA, or phi equal to EA, since integral dA will be equal to A. Here, A is the area of the flat face of the cylinder. Let this be equation 1. But according to Gauss' law, we have phi equal to Q in by epsilon naught. Here, Q in is the charge enclosed by the Gaussian surface. Since the surface charge density of the surface of the conductor is sigma, we have Q in is equal to sigma A. Let this be equation 2. Substituting equation 2 in the equation for electric flux phi, we get phi equal to sigma A by epsilon naught. Let this be equation 3. From equations 1 and 3, we have EA equal to sigma A by epsilon naught. Simplifying, we get magnitude of E equal to sigma by epsilon naught. If n cap is the unit vector in the outward direction normal to the surface, then we can write electric field strength in the vector notation as E is equal to sigma by epsilon naught into n cap. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. Inside the conductor, the electric field strength E is equal to 0. We know that the electric field strength E is equal to minus dV by dr. If V is constant everywhere inside the conductor, then dV by dr will be 0, and hence E is equal to 0 inside the conductor. This proves that the electric potential V is constant everywhere inside the volume of the conductor and has the same value as that on the surface. 6. A cavity inside a charged conductor is electrostatically shielded. We know that the electric field strength inside a charged conductor is 0. Hence, irrespective of the charge and the electric field configuration outside the conductor, the electric field in the cavity inside the conductor is 0, and the cavity will remain shielded from the electric field. This is called electrostatic shielding. When a car is caught in a thunderstorm, it is advisable for the driver and passengers to stay inside the car, since the inside of the car will be similar to a cavity in a conductor, and hence it will shield from the high voltage electric field that may get produced by the thunderstorm. We know that conductors are characterized by a large number of free charge carriers which move between the atoms of the conductors and also within the volume of the conductors. Metallic conductors have a large number of free electrons. When a metal conductor is placed in an external uniform electric field of strength, say E, we know that charge distribution takes place in the conductor due to the movement of the free charges, and the electrostatic induction occurs in such a way that in equilibrium, the electric field strength E' inside the conductor due to the induced charges is equal and opposite to the external field of strength E. Hence, the net electric field inside the conductor is zero, and the conductor is said to be in electrostatic equilibrium. Unlike conductors, dielectrics like rubber are those materials in which there are either practically no free charge carriers or free charges. Dielectrics are electrically non-conducting materials. A dielectric material can be made of either polar molecules or non-polar molecules. Polar molecules are those in which there always exists a separation between the average positions of the negative and positive charges in the molecule, irrespective of whether it is in an external electric field or not. Such a molecule is called a permanent dipole and will possess a permanent dipole moment. Water molecule is one such example of a polar molecule. In a water molecule, the center of the negative charge is at the oxygen ion, since it is the negatively charged ion, and the center of the positive charge is at the midpoint of the line joining the two positively charged hydrogen ions. These average positions of the positive and negative charges act as point charges, and hence the polar molecule behaves as a permanent electric dipole. As such, we can say that all polar molecules like water, hydrogen chloride, etc. behave as permanent electric dipoles. Therefore, even in the absence of an external electric field, such molecules possess a permanent electric dipole moment. Non-polar molecules are those which do not possess a permanent dipole moment like the polar molecules. Hydrogen and carbon dioxide molecules are examples of such non-polar molecules. In such molecules, the average centers of the positive and negative charges coincide. Hence, they do not possess an electric dipole moment in the absence of external electric field. Now let us see what happens when a dielectric with non-polar molecules is placed in an external uniform electric field of strength E. Due to this uniform external electric field, the positive charges in the molecules are displaced in the direction of the electric field, and the negative charges in them are displaced in the opposite direction of the electric field. Therefore, in the dielectric with non-polar molecules, the molecules now possess some induced electric dipole moment, and it is said to be polarized due to the external electric field. Now let us consider the case when the dielectric material is made of polar molecules. In the absence of the external electric field E, the polar molecules in the dielectric are such that their electric dipole moments are randomly oriented due to thermal agitation, and hence the total dipole moment is zero. Now when they are placed in the uniform electric field of strength E, we know that every dipole in it experiences a torque, which rotates the dipoles in such a way that they align in the direction of the electric field. Thus, the dielectric material with the polar molecules is said to be polarized. The degree of alignment of the dipoles with the external electric field direction depends on the temperature and also on the external electric field strength. In general, the alignment increases with increasing electric field strength and also with decreasing temperature. Thus, we observe that the dielectric material is polarized irrespective of whether it is made of polar or non-polar molecules, and they develop a net electric dipole moment in the presence of an external electric field. Linear isotropic dielectrics are those in which the induced dipole moment is in the direction of the external electric field and is proportional to the external electric field strength. Now, when this linear isotropic dielectric is placed in a uniform electric field of strength E, it gets polarized. Let us consider the polarization P of such materials, which is defined as the electric dipole moment per unit volume. For linear isotropic dielectric materials in a uniform external electric field, the polarization P is equal to psi E into E, where psi E is the electric susceptibility of the material. Now each small volume element of the linear isotropic dielectric having a volume dV has a net polarization equal to P dV due to all the dipoles in it in the direction of uniform electric field. Here, it is important to note that the net charge in each volume element will be zero. The resultant effect in the material due to the uniform external electric field will be the formation of an induced positive charge density plus sigma induced on the right face of the dielectric and minus sigma induced on the left side of the dielectric. This in turn causes a weak electric field of strength E' to be induced in a direction opposite to that of the uniform electric field of strength E. Therefore, the net electric field E0 in the dielectric will be equal to E minus E'. Thus we observe that the polarization effect causes a decrease in the net electric field within the dielectric. Dielectric materials, being non-conducting, are useful in many devices like capacitors, transformers, etc., because of their inherent properties. Capacitors are devices that store electric charge. A capacitor essentially consists of a system of two conductors close to each other and separated by an insulating medium. The conductors can be of any arbitrary shape. Generally, the conductors are given equal and opposite charge of magnitude Q. This can be done by connecting them to the two terminals of a battery. The conductors carrying the charge are referred to as the plates. And because the plates are charged, an electric field of strength E exists between the plates. The potential due to the plate having excess positive charge plus Q on it is V1. The potential due to the plate having excess negative charge minus Q on it is V2. The positively charged plate is at a higher potential than the negatively charged plate. Therefore, V1 is greater than V2. Hence, a potential difference exists between the two plates. Let the potential difference between the plates be V equal to V1 minus V2. As potential difference is measured in volt, this potential difference is referred to as voltage. We see that the total charge on the capacitor is plus Q plus minus Q equal to 0, as the conductors have charges of equal and opposite magnitude. It is a common practice to refer to the magnitude of charge on the conductors as the charge on the capacitor equal to Q, and the potential difference between the plates of the capacitor as the potential of the capacitor V. The electric field strength in the region between the plates increases as the magnitude of the charge on each plate of the capacitor increases. Then, the potential difference between the plates also increases. Since the potential difference V between the plates increases linearly with the charge on the capacitor, Q and V are proportional. Hence, the ratio Q by V is equal to C, where C is a constant, which is the capacitance of the capacitor considered. Let this be equation 1. Capacitance C of a capacitor is its ability to store electric charge. Greater the capacitance C of a capacitor, greater is the charge it can store, and hence greater is the electrostatic potential energy. The capacitance C depends on the size, shape, distance between the plates, and also the medium between the plates. The SI unit for capacitance C is the ratio of SI unit of charge to SI unit of potential difference, which is Coulomb per volt. It is also referred to as farad, named after the English physicist Michael Faraday. Generally, the submultiple units of capacitance like microfarad, nanofarad, and picofarad are used in practical applications than farad, since farad is a measure of higher magnitude. The capacitor in which the value of capacitance can be changed is called a variable capacitor. The symbols for a capacitor and a variable capacitor, as used in circuit diagrams, are as shown. It is important to note that a single plate can also act as a capacitor, assuming that the other is at infinity. For a capacitor having a very high potential difference between its plates, there exists a strong electric field between and around the plates. This strong electric field can ionize the surrounding air. The charges, so produced due to ionization, accelerate towards the oppositely charged plates of the capacitor and neutralize the charges on the plates of the capacitor, at least partly. Hence, we can say that the charge on the plates of the capacitor has leaked away due to the reduced insulating power of the intervening dielectric medium. When a sufficiently intense electric field is applied, the electrons of the intervening dielectric medium are torn away from their parent atoms, and the dielectric medium behaves as a conductor. This phenomenon is known as dielectric breakdown. Dielectric strength is defined as the maximum electric field strength that a dielectric medium can withstand without a breakdown of its insulating property. If the intervening medium is air, then the corresponding dielectric strength is 3 × 10⁶ volt per meter. If the distance between the plates is dr equal to 1 centimeter or 0.01 meter, then the corresponding potential difference V can be obtained by using the relation V is equal to EdR. Substituting the values of the above parameters, we see that V is equal to 3 × 10⁴ volt. Thus, we see that for a capacitor to be able to hold a large amount of charge Q, its capacitance has to be large enough so that the value of the potential difference V between the plates does not exceed the value of the potential difference and the electric field strength values corresponding to the dielectric breakdown. This means that there is a limit on the amount of the charge that can be stored by a given capacitor for a given intervening medium, without dielectric breakdown taking place. We also see that from the equation 1 that when the capacitance C is quite large, it can hold large charge Q at a relative low potential V. Since C and V are inversely proportional. The capacitors are used not only for storing charge, but in other applications as well. Some of their other uses are to tune the frequency of radio receivers, used as filters in power supplies. We have learnt earlier that a capacitor is an electric circuit element that is used to store charge temporarily. It, in general, consists of two metallic plates, separated and insulated from each other by a dielectric medium. Capacitors having different values of capacitances are used in power supplies, amplifiers, electric fans, motors, etc. It is not always possible to obtain capacitors with the desired values of capacitances. In such cases, the desired value of capacitance can be obtained by a combination of capacitors in a series or a parallel combination of multiple capacitors. Let us first discuss about the series combination of capacitors. Consider two parallel plate capacitors, A and B. The plates of A are labelled P and R, whereas the plates of B are labelled S and T. Let the capacitance of A be C1 and that of B be C2. The plate P of A is connected to the positive terminal of a battery, and the plate R of A is connected to the plate S of capacitor B. The plate T of B is connected to the negative terminal of the battery through a key K. This type of a combination of capacitors is called a series combination of capacitors. Let a potential difference delta V be applied across this combination by the battery. When the key is closed and the battery is connected to the combination of the capacitors, electrons are transferred out of the plate P of capacitor A and onto the plate T of capacitor B. Electrons are negatively charged and hence a negative charge is accumulated over the plate T. Let this charge be minus Q. Simultaneously, an equal amount of positive charge plus Q accumulates over the plate P. As minus Q accumulates on plate T, an equal amount of negative charge is forced off the plate S of capacitor B. Hence, the plate S has an excess positive charge, which is equal to plus Q. The negative charge, minus Q, leaving the plate S, travels through the connecting wire and accumulates on the plate R of capacitor A. Hence, the magnitude of charge accumulated on the plates of the capacitors connected in series is same. Let the potential difference across the capacitors A and B be delta V1 and delta V2 respectively. The relation between the capacitance of a capacitor C, the charge Q accumulated on it, and the potential difference across its plates delta V is given by Q is equal to C delta V. Let this be equation 1. Following the same expression, we get Q is equal to C1 delta V1 for capacitor A and Q is equal to C2 delta V2 for capacitor B. Simplifying the two expressions, we get delta V1 is equal to Q by C1 and delta V2 is equal to Q by C2. Let these be equations 2 and 3 respectively. In general, the total potential difference across any number of capacitors connected in series is the sum of the potential differences across the individual capacitors. Hence, the total potential difference offered by the battery, delta V, is equal to delta V1 plus delta V2. Let this be equation 4. Let Cs be the equivalent capacitance of the series combination of the capacitors. Then, we have charge Q is equal to Cs delta V. From this expression, we get delta V is equal to Q by Cs. Let this be equation 5. Substituting equation 5, equation 2 and equation 3 in equation 4, we get Q by Cs is equal to Q by C1 plus Q by C2. On simplifying the expression, we get 1 by Cs is equal to 1 by C1 plus 1 by C2. Let this be equation 6. The equation 6 gives the relation between the equivalent capacitance for the combination of two capacitors connected in series and their individual capacitances. The equation can be extended for any number of capacitors with different capacitance values connected in series. If n number of capacitors with capacitances C1, C2, C3, so on, up to Cn are connected in series, then the expression for equivalent capacitance of the combination Cs is given by 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus so on plus 1 by Cn. Let this be equation 7. To put in words, we say that when a number of capacitors are connected in series, the reciprocal of the equivalent capacitance of the combination is equal to the sum of the reciprocals of the individual capacitances of the capacitors in the combination. Let us now discuss about capacitors connected in a parallel combination. Consider the two capacitors A and B connected to a battery that supplies a potential difference of delta V such that the plates P and S are connected to the positive terminal of the battery and the plates R and T are connected to the negative terminal of the battery through the key. Such a combination of the capacitors is called a parallel combination of capacitors. When the key is closed, electrons are transferred through the wires and reach the plates. This transfer leaves the plates P and S positively charged and the plates R and T negatively charged. The energy required for this transfer is taken from the battery. The chemical energy stored in the battery is converted to the electrostatic potential energy associated with the separation of charge across the capacitors. The flow of charge to the plates of the capacitors stops when the plates acquire the potential difference equal to that supplied by the battery. The charge acquired by the plates of the capacitors is the maximum when the potential difference across them becomes equal to that applied. Let Q1 and Q2 be the charge accumulated on the plates of the capacitors A and B respectively. The total charge on the capacitors connected in parallel is equal to the sum of the charge on the individual capacitors. Hence, the total charge Q on both the capacitors A and B is equal to Q1 plus Q2. Let this be equation 8. As P and S are connected to the positive terminal of the battery, the potential at the plates is equal to the potential at the positive terminal of the battery. Similarly, the potential at the plates R and T is equal to the potential at the negative terminal of the battery. Hence, the potential differences across the capacitors connected in parallel are the same and is equal to the potential difference applied across the combination. Following equation 1, we have Q1 is equal to C1 delta V and Q2 is equal to C2 delta V. Let these be equations 9 and 10 respectively. Let Cp be the equivalent capacitance of the parallel combination of the capacitors. Then, we have Q is equal to Cp delta V. Let this be equation 11. Substituting equations 9, 10 and 11 in equation 8, and on simplifying, we get Cp is equal to C1 plus C2. Let this be equation 12. The equation 12 gives the relation between the equivalent capacitance for the combination of two capacitors connected in parallel and their individual capacitances. The equation can be extended for any number of capacitors with different capacitance values connected in parallel. If n number of capacitors with capacitances C1, C2, C3, so on, up to Cn are connected in parallel, then the expression for equivalent capacitance of the combination Cp is given by Cp is equal to C1 plus C2 plus C3 plus so on plus Cn. Let this be equation 13. To put in words, we say that when a number of capacitors are connected in parallel, the equivalent capacitance of the combination is equal to the sum of the individual capacitances of the capacitors in the combination. A Van der Graaff generator is a device that is used to build up very high voltages of a few million volts. This high voltage can build very strong electric fields, which can accelerate charged particles to very high speeds and high energy levels. Generally, this apparatus is required when conducting experiments involving the study of subatomic particles. To understand the principle behind the working of a Van der Graaff generator, let us consider a large conducting shell of radius r1 with a charge plus Q1 on it. This charge is uniformly spread over the conducting shell. For such a charged conducting shell, we know that the electric field strength inside the shell is 0. And the electric potential V inside the spherical shell has the same value at all points inside the shell, and V is equal to 1 by 4 pi epsilon naught Q1 by R1. Let this be equation 1. We also know that the electric potential at the surface of the spherical shell is equal to the potential inside the shell. Let us assume that there is another smaller concentric sphere of radius R2 with a charge Q2 on it. Now let us consider the potentials at the surfaces of the inner and the outer spheres. Let the potential at any point A on the surface of the inner sphere be VR2. This potential is due to the charge on both the spheres. Then VR2 is equal to 1 by 4 pi epsilon naught Q1 by R1 plus 1 by 4 pi epsilon naught Q2 by R2. Here, 1 by 4 pi epsilon naught Q1 by R1 is the potential due to the charge on the outer sphere. And 1 by 4 pi epsilon naught Q2 by R2 is the potential due to the charge on the inner sphere. The potential at any point B on the surface of the outer sphere is VR1. This potential is due to the charge on both the outer sphere as well as the charge on the inner sphere. Hence, V of R1 is equal to 1 by 4 pi epsilon naught Q1 by R1 plus 1 by 4 pi epsilon naught Q2 by R1. Here, 1 by 4 pi epsilon naught Q1 by R1 is the potential due to the charge on the outer sphere. And 1 by 4 pi epsilon naught Q2 by R1 is the potential due to the charge on the inner sphere. The potential difference between the inner and outer spheres is delta V equal to VR2 minus VR1. Substituting the values of VR2 and VR1 in the expression for delta V and simplifying, we get delta V is equal to 1 by 4 pi epsilon naught Q2 into 1 by R2 minus 1 by R1. We see that the potential difference delta V depends on value of Q2. Since Q2 is positive, the value of delta V is also positive. This clearly implies that the potential at the inner sphere is greater than the potential at the outer sphere. From the expression for delta V, we also see that the potential difference between the inner and outer spheres is independent of the charge Q1 given to the outer sphere. If we now connect the inner sphere to the outer sphere, charge flows from the inner sphere to the outer sphere, since the inner sphere is at a greater potential as compared to the outer sphere. Therefore, we can keep on adding charge to the outer sphere by supplying charge to the inner sphere as it flows from the inner sphere to the outer sphere. Therefore, the potential at the outer sphere keeps on rising until it reaches the breakdown field strength of air when it starts leaking off to the air. Due to the small charged sphere, which is within the large sphere, we can keep piling up larger and larger amount of charge on the latter. This is the principle of the Van der Graaff generator. The schematic diagram of the Van der Graaff generator is as shown. It consists of a hollow metallic conductor A, which is mounted on an insulating column. A pulley B is mounted at the center of the sphere A. Another pulley C is mounted near the base of the conductor. And C can be continuously driven by an electric motor or by hand in case of the device being used for demonstration. A belt of insulating material such as silk or rubber passes over the pulleys. As the pulleys move continuously, the belt also moves continuously. Two comb-shaped conductors, X and Y, having metallic needles, are mounted near each of the pulleys pointing towards the belt. The lower comb X is maintained at positive potential of about 10 power 4 volt by a power supply system. The upper comb Y is connected to the metallic sphere A. Because of the high electric field near the needles of the comb X, there is corona discharge, and the air near it starts conducting. The negative charges in the air move towards the positively charged needles because of attraction. The positive charges in the air move towards the belt due to repulsion and stick to the belt. The negative charges neutralize some of the positive charges on the comb X. The power supply keeps supplying more positive charge to the comb X, and effectively the positive charge is transferred from the power supply to the belt. As the belt moves, this positive charge on the belt is carried up, and when it reaches near the upper comb Y, corona discharge occurs again, and the air starts conducting. The negative charges in the air moves towards the belt, and the positive charges in the air move towards the needles of the comb Y. The negative charges neutralize the positive charges on the belt. The positive charges in the air, which have moved to the comb, are effectively transferred to the sphere A. Effectively, the positive charge on the belt is transferred to the sphere, and in a very short duration of time, the positive charge on the sphere moves to the outer surface and spreads uniformly. Thus, the device continuously transfers positive charge to the sphere A, and hence, its potential keeps on increasing. The potential builds up till the corresponding electric field reaches close to the breakdown field of air, which is of the order of 3 × 10⁶ volt per meter. The limiting factor on the value of the potential of the sphere is the radius of the sphere. When the electric field outside the sphere A is just sufficient for dielectric breakdown of surrounding air, no more charge can be transferred to the sphere A. A sphere of radius r equal to 1 meter can be raised to a potential of 3 × 10⁶ volt by this method. The potential can be further increased by placing the sphere in a highly evacuated chamber, in which case there will not be any air surrounding the sphere.